Hi, everyone. My name is Yuchen Zhang from Stevens Institute of Technology. And it is my great honor to present our work, Debloating address Sanitizer today. The co-authors are Chengbin from Nanjing University, Professor Georgios Portokalidis from Stevens Institute of Technology, Professor Nikos Triandopoulos from Stevens as well, and Professor Jun Xu from the University of Utah. So before I started presenting our work, I would like to give some background information about sanitizers, which are dynamic code analysis tools. Here are the current supported sanitizers by Google. The first one is address sanitizer, or so-called ASan, for detecting addressability issues, and the thread sanitizer to detect the data race and deadlocks, and memory sanitizer for detecting use of uninitialized memory, and UBSan for detect undefined behaviors. And our work is focusing on optimizing and improving the performance of address sanitizer. So what is ASan? It is the most popular sanitizer for vulnerability detection, which focuses on memory safety violations in heap, stack, and global objects. The mechanism for ASan is to insert poisoned red zones around objects and report error when program access the forbidden bytes. So here from the graph, we can see for each heap, stack, or global objects, they are surrounded by red zone. And if the program tries to access those red zones at runtime, ASan will abort the execution process and report error with a detailed bug report. Next, I'm going to present the motivation of our work, that even though address sanitizer is powerful, but there's still trade-offs for using ASan. That is, ASan causes high runtime overhead. And from SPEC CPU2006, the average overhead that ASan brings is 107.8%. And the instrumented applications testing also costs a lot in compute resources. Quoted from the sanitizer maintainer in Google, in the long run, faster binary equals or greater than more bugs caught. So driven by our motivation, we first present a study to answer the question, what brings the overhead of ASan? The answer is sanitizer checks. They are the primary source of ASan overhead, which is attributed to an overhead of 86.5%, which is 80.8% of all the overhead. Our study also dissect the rest of ASan overhead, where they come from. And for details, please refer to our paper. As we indicated in the previous slide, the sanitizer checks are the primary source of address sanitizer performance overhead. Here, let's see from an example. On the left side, we have an array with size 10, and then we're trying to access the 10th position of that array by indexing. And on the right side is the corresponding LVM-IR code. The instructions that in red box is the sanitizer check inserted by ASan. And please note, for every memory accessing, ASan will insert sanitizer check. Therefore, the runtime overhead of ASan goes up. Next, I'm going to present our tool, Debloating address sanitizer, or we call ASan --. We implement a group of optimization strategies to reduce the sanitizer checks of ASan. First, we remove the unsatisfiable checks. Second, we remove the recurring checks. Then we optimize the neighbor checks. And finally, we optimize the checks in loops. Our tool, ASan --, can reduce address sanitizer runtime overhead while keeping the bug detection ability. And our tool is applicable to SPEC CPU2006 and the Chromium, showing the scalability. Finally, we integrated our optimizations into LVM for high usability, and thus no extra cost for building the tool. Now I'm going to talk about the details about our proposed solution for optimizing address sanitizer. First is the removing unsatisfiable check. Let's see an example together. On the left side, we have a buffer with size 20 in line 2. And we then try to access the I position by indexing into the buffer. So can this buffer be overflowed? The answer is no. The buffer will never overflow because in line 4, the if statement has already guaranteed that the value of I will always less than or equal to 10. So the index to buffer will always inbound. And thus, the sanitizer check that inserted by ASan in line 5 can be safely removed. Next is removing the recurrenting checks and how we do that. Let's first define what is recurrenting check. From the example on the left side, we can see in line 3, ASan check 1 and in line 5, ASan check 2 are checking the same value, pointer p. And check 1 dominates check 2. In another word, if check 2 will be executed, no matter what, the check 1 will be executed first. Therefore, ASan check 2 in line 5 is recurrenting check, and the safety of pointer p has been guaranteed by check 1 in line 3. So we can also safely remove the redundant check without losing any safety. And as for optimizing neighbor checks, if there are two memory access that accessing the neighbor memories, such as accessing structured fields in the example on the left, we can merge those ASan checks in line 6 and in line 8 into one check. We also implement a fast, slow path strategy to secure the detection accuracy. The fast path will check multiple shadow bytes at once, and if it fails, the slow path will be triggered and do the regular ASan check on each shadow byte, then abort the current execution. Finally, we also optimize the sanitizer check in loops. There are two scenarios we apply our strategy. First, if the indexing value to a buffer is monotonic, increasing or decreasing, as shown in line 6 on the left side, we merge the check by checking multiple shadow bytes at once, as I presented in the previous slide. And the second scenario is the sanitizer check is repeating multiple times on the same value, which is not cost effective, as for in line 9. The pointer PTR2 will not change during the loop iteration. So we move the check in line 7 out of the loop and only execute once. By this way, we can efficiently reduce the number of execution times of same sanitizer check. After briefly introducing our tool ASan-, now it's time for evaluations. First part is the performance overhead analysis. By applying all of the optimization strategies on SPEC CPU2006, the runtime overhead that ASan brings drops from 107.8% to 63.3%. And for Chromium, the runtime overhead drops from 117.8% to 75.8%. The performance evaluation shows our tool ASan-, can efficiently reduce the overhead that caused by ASan. Next, I'm going to present the bug detection capability. After applying our tool on 3 benchmarks, the Julia test suite, the Linux Flow project, and the Chromium project. For all benchmarks, we compiled with both ASan and ASan-, then comparing the detected bugs result. Finally, we verify that ASan and ASan-, achieve the identical results. Our tool can also bring extra benefit to fuzzing. It is very popular to combine fuzzing and address sanitizer together for bug detection nowadays. And fuzzing benchmarks compiled with ASan-, increased the execution speed of AFL by 42.1%, and the increase of execution speed leads to a growth rate of 5% in branch coverage. In conclusion, adding ASan in applications can hurt the performance, and the Sanitizer check contribute the most. But our tool, ASan-, can efficiently reduce the performance overhead. Meanwhile, maintain the capability, scalability, and usability of ASan. It can benefit the applications that compiled with ASan and reduced the overhead of ASan by 41.7% on SPEC CPU2006 and by 35% on Chromium. In addition, it also benefits fuzzing test with ASan-enabled applications and increased the execution speed and the branch coverage. Our work passed the artifact evaluation and got all the badges. Now has been open sourced on GitHub. Please refer to the link for more implementation details. And thanks for listening. I'm now opening for any questions.